Hello, everyone. Welcome to the Graphics Programming Virtual Meetup. Today, we will continue reading physically based rendering book and start talking about reflection models. So this chapter defines a set of classes for describing how the way light scattered at surfaces. So recall previously that we have bidirectional reflectance distribution function, BSDF, which describe light reflection at the surface, and also BTDF to describe transmission at the surface, and BSDF to encompass both of these. And in this chapter, we will start by defining a generic interface to these surface reflection and transmission functions. Surface reflection models come from a number of sources, measured data. So yeah, a lot of reflection distribution properties have been measured in the lab. Such data may be used directly in tabular form or to compute coefficients for a set of basis functions. Phenomenological models, which are equations that attempt to describe the qualitative property of real-world surfaces. They can be remarkably effective at mimicking them. And these type of BSDFs can be easy to use for like artists because they can have intuitive parameters, like roughness, metallic, stuff like that. Simulation. So sometimes low-level information is known about the composition of the surface. So example, we might know a paint is comprised of colored particles of some average size suspended in media, or that a particular fabric is comprised of two types of thread with known reflectance properties. In this case, a pre-process could be simulate the behavior of light within the metal structure to fit the approximate BSDF. Alternatively, simulation could occur when rendering. Wave optics, which is usually more advanced than what we do, which is geometric optics. So wave optics, some reflection models can be derived using a detailed model of light treated as a wave and computing the solution to Maxwell equations. They are mainly used when the scene contains geometric detail at the micrometer levels that make wave optical behavior readily apparent. And then geometric optics. So as with the simulation approach, if the surface low-level scattering and the geometric property is known, then a closed-form reflection model can sometimes be directly derived from these descriptions. And geometric optics makes modeling light interaction with the surface more tractable because complex wave effect like diffraction are ignored. This chapter describes implementations of a number of such models. And then in 14.3, introduce a reflection model based on simulation of light scattering in layered materials. And further reading sections give more pointers. And the important component of surface appearance is the spatial variation of reflection and transmission property over the surface. And yeah, texture and material classes in the next chapter. Yeah, next chapter will address that problem. Yeah. While the abstraction presented in this chapter will only consider like scattering at a single point on the surface. Both the BRDF and the BTDF only model scattering from light that enter and exit a surface at a single point. Or like subsurface scattering, like for surface exhibiting meaningful subsurface light transport, more complete simulation of light scattering inside the material is necessary. Like this in chapter 14, they will talk about how to do that. So basic terminologies to describe reflection from surfaces. So to compare the result visual appearance, we will classify reflection into following four broad categories: diffuse, glossy specular, perfect specular, and retroreflective. Most real surface exhibit a mixture of these four behaviors. Diffuse is like equally scatter light in all directions. Perfectly diffuse material surface is not physically realizable. Near diffuse surface include like dull chalkboard and matte paint. Glossy specular surface such as plastic or high gloss paint scatter light in a preference. Sorry, I don't know how to pronounce that. Scatter light in a set of reflected direction. They should blur the reflection of other object. Yeah, so it's much more concentrated. And perfect specular surface scatter incident light in a single outgoing direction. So yeah, it's like that. So it's like a mirror. And the mirror and glass are example of perfect specular surfaces. And retro-reflective surfaces like velvet or the Earth's moon scatter light primarily back along the incidence direction. Oh, interesting. I don't know about that. Okay. So given a particular category of reflection, the reflectance distribution function may be isotropic or anisotropic. And with isotropic material, if you choose a point on the surface and rotate it around its normal axis of that point, the distribution of light reflected at that point does not change. Yeah, diffuse materials like paper or wall paint are usually isotropic. Yeah, because it's scattered to all the directions equally. In contrast, anisotropic materials reflect a different amount of light as you rotate them in this way. Example of anisotropic materials include hair and many types of clothes. Industrial processes such as milling, rolling, extrusion, and 3D printing also tend to produce highly anisotropic surfaces. Extreme example including brushed metal. So BSDF representation. So there are two components of PBRT representation of BSDF. So they have a BXDF interface and its implementation and the BSDF class. The former model specific type of scattering edge surfaces, while later provide a convenient wrapper around the pointer for a specific BXDF implementation. And the BSDF class also centralized general functionality so that the BXDF implementations do not individually need to handle it. And it records information about local geometric property of the surface. Geometric settings and conventions. So reflection computation in PBRT are performed in reflection coordinate system, where the two tangent vectors and normal vector at point are being shaded aligned with X, Y, Z axis, respectively. So two tangent vectors X, Y, okay, and normal and Z. So normal points upward, I think, yeah. All direction vector pass to and return from the BXDF evaluation and sample routines will be defined with respect to this coordinate system. So they will be transformed, and output will be transformed, inverse transformed, I think. So section 3.8 introduced a range of utility functions that evaluate the trig function of unit vectors expressed in Cartesian coordinates matching the convention used here. They will be used extensively in this chapter as quantity like cosine of the elevation angle plays a central role in most reflectance models. The shading coordinate system is defined by orthonormal basis vectors ST and N, which is two tangent and the normal. We will orient these vectors such that they lie along with X and Z axis in this coordinate system. And there is a direction vector omega in rendering space that in rendering space transformed into the shading coordinate system before any of those methods are called. So it's sometimes useful to check whether two direction vectors lie in the same hemisphere with respect to the surface normal in the BSDF coordinate system. So the same hemisphere function perform this check whether they're just check whether they are zero. Sorry, their z axis have the same sign. So if like one is point upward and another is downward, then it will have different sign. Additional convention that are important to keep in mind. Incident light direction omega I and outgoing viewing direction omega O will both be normalized and outward facing after being transformed into a local coordinate system at the surface. Oh, interesting. So even the incident light will be outward facing. Yeah, that's definitely something to keep in mind. Yeah, in other words, the direction will not model the physical propagation of light, which is helpful in bidirectional rendering algorithm that generate light paths in reverse order. The surface normal always point to the outside of the object, which make it easy to determine if light is entering or exiting a transmissive object. Yeah, if the incident light direction is in the same hemisphere as and the light is entering, otherwise it is exiting. The normal may be on the opposite side of the surface. Then one or both of the omega I and omega O. Yes. Yeah. If they're coming from back and then also exiting at back, then the normal will be opposite for both. Unlike many other render, PBRT does not flip normal to lie in the same set as omega O. So local coordinate system used for shading may not be exactly the same as the coordinate system returned by the shape intersect routine from chapter 6. It may be modified to achieve effect like bump mapping. So modified by the material, basically. So BXDF is again like tagged pointer. This bunch of different implementations. And there's a flag to list previously to the different categorizations and distinguishes reflection from transmission. So yeah, reflection, transmission, diffuse gloss, see, and yeah, specular. And also a bunch of composite definition using the OR operation, the bitwise OR. Yeah, like this. And they have a bunch of utilities to track the flag. And key method of BSDF provides F, which returns the value of the distribution function or the given pair of directions, so the input and output. The provided direction must be expressed in local reflection coordinate system introduced. So this interface implicitly assumes that lighting different wavelengths is decoupled. Energy at one wavelength will not be reflected at different wavelengths. Yeah, in this case, the effect of reflection can be described by per wavelength factor written in the form of sampled spectrum. Fluorescent materials that redistribute energy between wavelengths would require this method to return a matrix to include the transfer between n spectral samples of sampled spectrum. I guess they just don't support that in this interface. Neither constructors nor method of BSDF implementation will generally be informed about the specific wavelengths associated with sampled spectrum entries. They do not need this information. We talk about constructor yet? Not yet. Also take a transport mode enum that indicates whether the outgoing direction is toward the camera or toward the light source. It is necessary to handle cases where scattering is non-symmetric. We will discuss further in 9.5.2. The XDF must also provide a method that uses importance sampling to draw a direction from distribution that approximately matches the scattering function's shape. So importance sampling is crucial for efficient Monte Carlo integration. It is also the only way to evaluate some BSDFs. Interesting. Oh, yeah. Yeah, perfect specular objects like mirror, glass, and water only scatter light from a single incident direction into a single outgoing direction. Yeah, such BXDF are best described in direct delta distribution, which will be zero except a single direction where the light are scattered. So yeah, F and PDF will just be zero, basically. So not useful to describe them as a probabilistic distribution. So implementations of sample F method should determine the direction of incident light omega I given the outgoing direction omega O. And the return value of BXF for the pair of directions. Take three uniform samples in the range of 1 to 0, 0 to 1, and while UC and U parameter. Implementations use however they wish, so it's generally best if they use a 1D sample UC to choose between different types of scattering and the 2D sample to choose a specific domain. Using UC and U0 to choose a direction would like to give an inferior result. Now, because the 2D sample generate together, I think. Yeah, since the UC and U are not necessarily jointly well distributed. Not all sample values need to be used, and BSDF that need additional sample value must generate them on the fly. Hey, I see your cat too. So yeah, I think, for example, for purely diffused material or purely specular, then they probably don't need they don't need UC. They just need U. Potentially counterintuitive direction convention. The outgoing direction omega O is given. Oh, yeah, and the implementation then samples an incident direction omega I. The Monte Carlo method in this book constructs light passes in reverse order. Yeah, counter the propagation direction of the transported quantity, which motivated this convention. Calling this method must be prepared the possibility that sampling failed. Then it is optional. And sample generation can optionally be restricted to the reflection or transmission component, while sample flags parameter. A sampling failure will occur in invalid cases. For example, if the caller requests a transmission sample opaque surface. Yeah. If the sampling succeeds, the method returns a BSDF sample that include the value of BSDF F. Yeah, so it's the spectrum. Sample direction, the PDF measured with respect to the solid angle, and a flag to describe the characteristic of particular sample. Is it this flag? It's this flag. BXDF should specify the direction omega I with respect to local reflection coordinate system. And sample F will transform this direction to rendering space before returning it. So some BXDF implementation, notably the layered BXDF, generate samples via simulation following a random-like path. And the distribution of paths that escape is the BXDF's exactly distribution. But the returned F and PDF are only proportional to their true value. In this case, the special handling in the lab transport algorithm, which is indicated by the PDF, is proportional field. So in this chapter, we will just ignore it for now. And this bunch of methods to query the property of the sample, which just query the flag. And the PDF method returns the value of the PDF given a pair of direction. Which is useful for multiple important sampling, yes. And hemispherical reflectance. Yeah, with the BXDF methods described so far, it's already possible to implement methods that compute the reflectance of BXDF by applying the Monte Carlo estimator to the definition of reflectance from equation in chapter 4. Yeah. The first variant of BXDF rho computes a reflectance function rho. Its color is responsible for determining how many samples should be taken and for providing a uniform sample values to be used in computing the estimate. So yeah, we just put it in a for loop, which is a sum, and divided by the size and the in the for loop where each term is calculated by the BSDF F times the cosine term and divide by the PDF. Yes. Yeah, it's here. Yeah, if we have a sample, we just add them by the BSDF times the cosine and then divide by the PDF. Hemispherical reflectance is found in the second BSDF row method that evaluate equation 4.3. Unfortunately, I just don't remember it at this point because it's maybe a year ago. What's it? I think I will skip this part because I don't understand it. Sorry about that. And then delta distribution in BSDFs. So several BSDF model in this chapter use the direct delta distribution because they are perfectly specular materials. Yeah, direct delta distribution defined there as zero for all the point where x is not zero, or in this one particular point, it's not even defined, it's just an integral. Integral to be one. Generating a sample from such distribution is trivial since there is only one value to take. However, sampling alone is not enough. Good method like sample F and PDF also provides sampling density and is considerably less clear what value should be returned here. Yeah, because a delta distribution is not a true function. It constitutes a limit of it's a limit basically. If you squeeze it closer and closer, squeeze that box closer and closer where its width gets smaller and smaller, but its height gets larger and larger. So the value of delta zero must be infinity. But this theoretical realization does not easily translate to code. Return an infinite or very large PDF value is not going to lead to correct results from the render. To resolve this conflict, the BSDF may only contain matched pairs of delta function in their FR function and PDF. So the PDF factor into a remainder term and the delta function involve a particular direction omega prime. If the same holds true for the FR, then the Monte Carlo estimator divided by FR by the PDF will never require evaluation of the delta function. Yeah, it's basically a special case. Just we divide the delta. So implementation of perfect specular material will always return a constant PDF of 1, where sample F generate a direction associated with the delta function. with understanding that the delta function will cancel in the estimator. Respective PDF method should return 0 for all directions, since there are 0 probability that another sampling method will randomly find a direction from the delta distribution. Yes. BSDF. So BXDF class implementer performs all computation in local shading coordinate system. That is most appropriate for this task, but random algorithm operates in rendering space, so a transformation between these two spaces must be performed somewhere. And BSDF is a wrapper around BXDF that handle this transformation. So it has a BXDF and also a coordinate frame. And the shading frame is calculated from the normal and DPDUS. What is that? The shading normal. Oh, DPDUS is like the tangent. And here is a discussion of the geometric normal, which is defined by the surface geometry, and the shading normal, which is the per vertex normal, and bump mapping, which will be defined by the material on top of the geometric normal. The default constructor create BSDF with null pointer value to BXDF, which is useful to represent transitions between different media that do not themselves scatter light. And a full method check whether BSDF represented real material interaction. Yeah. And flags provide further information about the high level properties. And BSDFs provide methods that perform transformations to and from the reflection coordinate system using BXDF. It just calls the shading frame method. There are cases in which the omega O direction lie exactly in the surface tangent plane can lead to a nan value in the BXDF implementation. So sampled spectrum just return the zero valued sample spectrum if it detect this case BSDF. Yeah. Also, BSDF also provides a second templated F method that can be parameterized by a underlying BSDF. If the caller knows a specific type of BXDF, it can use this variant directly without involving the dynamic dispatch. This approach is used in the wavefront rendering path. It's group evaluation based on underlying BXDF to benefit from vectorized execution on the GPU. And it casts to the provided type. Oh, it still checks though. Yeah, it still checks. And the sample F method similarly forward the sampling request to the BXDF after transforming the omega O direction to a local coordinate system. Yes. And if the BXDF implementation returns a sample that has zero valued BSDF or PDF or incident direction in the tangent plane, this method returns an unset sample value. This allows the calling code to proceed without checking these cases. Just for corner cases, it just returns the unset sample value. And BSDF PDF follows the same pattern. Just delegate. Yes. All right, I think we are done with this part.